Welcome to this short talk about the discovery of correlation-driven electronic nematicity in the Dirac semimetal, barium nickel disulfide. I'm Christopher Butler. If you're interested to learn more about this topic, you can find it published as shown here. So, barium nickel disulfide is a quasi-two-dimensional material with layered nickel square nets. In this kind of system, we should expect electronic correlations to play some significant role. As well as this, at the bottom here, I'm going to highlight two interesting features of the surface electronic structure. Firstly, here on the left, a topological Dirac node between gamma and M in the surface Brillouin zone. And around the X point, also this electron-like band, which I'll discuss more as we go along. In this work, we used a low-temperature scanning tunneling microscope, or STM, to image the surface, the cleaved surface of a barium nickel disulfide crystal. So on the left here is an STM topography image of that surface. So in barium nickel disulfide, the electronic density of states near the Fermi level comes almost entirely from the nickel atoms. So that means that the square lattice that we see in the STM image represents the nickel square lattice, and specifically what we call the nickel A here, which is the uppermost of the two nickel square lattices. And this means that the STM is allowing us to directly visualize this two-dimensional nickel square net system, which is a nice correlated electron system. So STM can also do tunneling spectroscopy measurements, which are resolved both in space and in energy. So here we do such a measurement in a small field of view like this. Now the tunneling spectroscopy gives us a conductance that's proportional to the local density of states. So these are images of the local density of states at certain energies. And what we see here is a striking feature, which is an unexpectedly low symmetry in the density of states. So the symmetry is reduced from C4, which is expected for this surface, down to C2. In fact, a pair of C2 striped patterns. So each one of them is commensurate with the nickel lattice along one of the nickel bond chains in a given direction. So taken together, we call these patterns an example of bond order nematicity. And here nematicity refers to an electronic phase which preserves the lattice translational symmetry but breaks the rotational symmetry. And given such a bond order nematic pattern, we can do a suitable sampling of the density of states in real space that allows us to disaggregate the energy resolved spectra in such a way that we can distinguish spectral features, each of which correspond to one of these striped patterns. And we see that those spectral features appear to have a splitting of 12 millielectron volts between them. So this feature will be explained hopefully by the end of this talk. So when we see this kind of bond order pattern in real space, we can infer that there is a corresponding pattern in K-space, namely a D form factor throughout the Brillouin zone, like this. So this is in K-space. So what can STM do to resolve and to characterize features in K-space? We can examine what we call quasi-particle interference, which is resulting from scattering in the electronic structure. So again, we image the density of states in this time a large field of view and take its Fourier transform. And the signals in this Fourier transform represent scattering that is allowed in the band structure. And of course, the measurement is energy resolved, so we can also see the dispersion of these scattering events. So for example, these two linearly dispersing scattering events correspond to scattering between Dirac cones. There's another scattering event here that approaches the endpoint, which is the reciprocal lattice vector, and that will be discussed more. That is scattering between the electron bands around the X points. Now, as well as this measurement, we can also do calculations that help us to fully understand all of the scattering signals that we see above. So in order to highlight the symmetry breaking in the data, what we've done here is take line cuts in two perpendicular directions. We can see the dispersion of the scattering in each direction, and we can do some fitting analysis to extract quantitative information. And now if I take these two plots for the dispersion in the two different directions and overlay them as shown here on the left, I can see that in the two different directions the scattering is the same almost everywhere, except in this scattering branch, which is related to scattering between the electron bands around X. And as it approaches the reciprocal lattice vector, there's a splitting between the two branches that approaches 12 millielectron volts again, which is the same as we saw in the previous observation. So this reinforces this idea that in the Brillouin zone there is this d form factor pattern, so that in two different directions, scattering events that are supported in those two different directions happen at slightly different energies. Okay, so how can this be explained? Well, here Kontani Sensei's group from Nagoya University come to the rescue, and they are able to use this density wave equation framework to make numerical calculations, starting from a tight binding model, but going beyond the mean field contributions to include so-called non-local vertex corrections, including these Aslamazov-Larkin terms, which describe spin fluctuations. And they have shown that the interference between spin fluctuations can result in this nematicity, this symmetry breaking. And this methodology is described more fully in these papers, if you're interested. Okay. So the final objective here is to numerically calculate the form factor, which is represented here as f of k, for each of the relevant orbitals. And once those are calculated, they appear as shown here. Now these are energy shifts that are applied throughout the Brillouin zone, and if we apply those to the band structure we see around the X point, the bands indeed split as shown here. So this splitting circled here is sufficient to explain both of the observations that I've mentioned so far in the spectra and in the scattering. And in fact, these two manifestations actually both coming from this splitting of the band around the X points. So both of these observations have been successfully explained. This brings us on to the conclusion. So just to run through the overview again, our STM images, including images of the density of states, show an unexpected symmetry breaking from the expected C4 down to C2, and this is called a bond order nematicity. And this nematicity can be explained by a d form factor. Here it's worth noting that the other interesting feature in the electronic structure was this Dirac cone. But because the Dirac cone lies on the line between gamma and m, which is the node of the d form factor, that Dirac node and the Dirac cone are unaffected by this d form factor nematicity. So the mechanism underlying the d form factor nematicity is thought to be the interference of spin fluctuations. So as shown in this cartoon here, this bond order arises from interference between spin fluctuations, and this means that the nematicity that we've observed can be attributed to this effect, which is a correlated electron effect. That brings us to the end. Thank you for listening.